Okay, so we want to work on 11.1. This is three-dimensional coordinate system. We're just going to introduce this, get a little bit of familiarity working in three variables, what that looks like graphically. Probably take a little bit of time to get used to, but it's not that bad of a concept once you're... Okay, so first thing. Now, when you do R3, this is the 3D coordinate system. This R here in this kind of funny, like a math blackboard font maybe, but this R, that's real numbers here. Sometimes you'll see a Z written in this font, or a Q. Z would be integers, Q would be rational numbers. The 3 just means there's 3 coordinates. So again, R, this just means real numbers. And what's going to happen here are 2, that'd be like the XY plane. And really, X and Y, same thing in R3 as they work in R2. Z, this is our new variable. It will have an axis, so you've got your flat plane for xy. The z-axis is sort of perpendicular to those. It gives you maybe a height if you view xy as sort of a flat plane. Z gives you a height. Now, there's one kind of trick to this, and we have to obey the right-hand rule here. Essentially, what we're saying is that if x and y give us a flat plane, we want to, depending on what x and y, how they are oriented with each other, that's going to define the positive direction for z to be either up or down. Here. So I want to be consistent with that here. And the right-hand rule just means that if your fingers on your right hand curl from the positive x-axis to the positive y-axis, then your thumb should point in the direction of the positive z-axis. So it's just some sort of, I guess, anatomical way to remember sort of which direction the z-axis should point. So let's just do some examples here. So if this was x and y, now x and y, these are the positive axes. They should be at right angles, but we're going to be sort of from a 3D perspective, so it doesn't quite look like a right angle, perhaps. So what we're going to say here is that if we went and our fingers curled from x to y on our right hand, that's going to end up with your thumb pointing upward. So if this is your x, this is your y, z has to point upward. Another example is we could replace where we start with x and y here. Now if you did that and you had to curl your fingers from x to y, you'd end up with the z pointing down, your thumb down, so the z points down. Note that essentially what's going on here is I'm taking this picture here as sort of a defined axis direction, and I'm just kind of rotating that and flipping it over and getting here. So if you took the x, flipped it to the y, the z would have to flip as well. Essentially, you've got one stationary axis directions, and you're just rotating those in space. And the right-hand rule basically allows us to say, well, if I know what x and y do, it tells me which way z goes, so that I don't have to think about this as rotating in space. Here's another example. Here we have an x and a y here. So if I went from x to y rule, I'm going to get as a sort of, if my x and y fingers swirl, I'm going to get a vector pointing sort of out from there. Now this one, we're going to think of z as up, x is sort of to the right, and y is back in some sense. So this is going to be a sort of xy plane, maybe as we're used to it. If you view the x and y as a plane on, say, the top of a table here, z is going to point straight up. Here, x would be the right, y would be back along the table. Here's another example. Here, x is going to be the right, and now we're going to think of y as up. If you think about that, and you did it right hand, and you sort of curled your fingers from x to y, the z is going to have to point sort of out towards you. It's going to look like this in sort of 3 dimensions from a perspective viewpoint. So the idea here again is that all of these represent manifestations of this first one, the x, y, z, with z up, x sort of down on the left, y to the right. It's just those are all rotated around in certain ways here to make that work. Okay, so there's our coordinate systems. Now we can do equations in R3. We're just going to do some examples here. We're going to start with y equals 0. So the idea here is this is the set of all. Now note we have to say in R3, set of all x, y, z. This could be an equation in R2, which would just be x and y here. But now we're going to do x, y, and z, and we just want y to be 0, and x and z can be whatever they want. This is going to end up be a plane. So y is 0. X and z can take on any values they want. So a picture of this here. So I'm using Mathematica to draw these. The command is up there at the top. I'm not so much concerned about that. There's various commands depending on the kinds of things we'll be drawing here. I'm not worried about that now, but here's our picture. So we've got our axes here. You'll notice if we twirl this around a bit, you have your positive x, positive z. That's maybe oriented a little bit funny. But you see, you sort of take on all the possible x and z values. And if we twirl this around here, the y-axis runs this way. Here's positive y, where the letter y is, to negative y. You can see the -5 there. This -5 is on probably the x-axis here, the one there. So it's not part of the y-axis. But you can see here that sort of all this plane exists when y is 0. So you set y equal to 0, and you get a plane. Now, this particular one is known as the xz plane. So we have two variables in a plane like x and z. That means the third variable is 0. So this is assuming we're in R3. So you could talk about the xy plane would be where z equals 0, or the yz plane would be where x equals 0. Another equation example, we have x equals 2. Now this is going to look very much the same as the previous one, kind of rotated around, but once we rotate the graphic, we're not really going to notice that. But now instead of sort of our variable that we're fixing being 0, we're going to fix that variable at 2. So in this case, x has to be 2, and then y and z can take on whatever values they like here. So this particular picture is down here. You can see here on this graph, x goes 1, 2, and you get your whole plane out there, and you get sort of all the y and z values. So if I just rotate this around, where my x-axis sort of goes into the picture, and I just more or less just see the y and z, I get the whole plane. So it would extend outside of this box, give you the whole plane. So same thing, but now there's sort of a gap between the plane and the, well, y and z axes, that'd be the yz plane. So it's not right on the axes, it's sort of off a bit. Okay. Another example, you can put this comma here, and that's going to mean where you want the set of points that satisfy x equals 2 and z equals 3 at the same time. So what we're going to get is we are going to fix x as 2, fix z as 3, and then y take on whatever value it wants. So note here we've got one variable that's sort of varying as we go along. Previously we had 2. What that's going to mean is we're going to get a one-dimensional object instead of a two-dimensional object. The plane would be sort of two directions, so a plane would be two-dimensional. We only have one direction we can go. What that's going to look like here, it's going to look like a line here. So we had, I forget exactly what we had. We had x is 2 and z is 3. So when x is 2, you note here, you can rotate this around where we just see x and z. We go 1, 2 for x, 1, 2, 3 tick marks for z. So this is the point 2, 3 if we're just in the xz plane. But then as you let y vary, sort of y can take on whatever value you want. So you go along the y plane, or along the y-axis, you get all the possible values here. But every x is 2, every z is 3. Oh, so there's some equations. Here's some more. A little more complicated. We're going to do x squared plus y squared equals 4. Now in R2, so just x and y, this would be a circle. So we're saying here is the x and y's behave as a circle of radius 2. 2 squared would give us the 4. But then z can be whatever you want. So this is actually going to be a, well, so if we only consider x and y, we get a circle of radius 2 centered at the origin. Z can be anything. So this is going to give us a cylinder whose axis is along the z-axis. So the picture of that, so along is right here. I'm going to rotate this around. You can see sort of a tube or a cylinder here. Note it's only the outside portion that shows up in our graph. And if you sort of rotate this around in the xy, note x positive this way, so we could flip this around and get sort of the typical situation we're used to. Here, it's really the same picture. Now this should be a circle, but Mathematica has some kind of perspective angle thing, so there's some sort of thickness here, and it's just because you're seeing sort of part of the tube as you go along. So we're having a little bit of trouble getting this to be exactly a circle, but it would be, really. And if you rotate this around, you can see in the z direction, here I guess positive z, we sort of take on every possible z. So for every z, we get a circle. So like this line here, you cut this, would be a circle. This line, if you sliced through, would give you a circle. All circles radius 2, centered, well, on the z-axis, effectively, the appropriate point. We can make this a little more complicated. Do x squared plus z squared. No, we switched y squared to z squared. So x squared plus z squared equals 9. So radius 3 centers the origin. Y is our axis here of our cylinder now, but then we also want y to be fixed as 0. So if we just did x squared plus z squared equals 9, that's going to give us a cylinder axis along the y-axis. We can look at a picture of that here. So this is just the first equation. So it's a cylinder here. This time note here, I guess the positive y direction. That's our orientation here. The one we had before, it was in the z direction. It was sort of the long part of the tube in the z. Now we've got in the y. Radius is different, but that's going to be kind of hard to pick up with these drawings, just sort of roughly. So that's there. Now if you do y equals 0, that really forces your solution to be in the xz plane. So what we get here is we take this cylinder, we chop this at y equals 0. Again, y is going to go this way. Here's y equals 0. We're going to chop this, and we're going to get one circle here. So note here that's y equals 0. So you can see the y's go to 0. And then if you rotated this around, you're going to get a circle in the xz here. Now, this is a little tricky to see sometimes, or maybe visualize this circle in three-dimensional space. Here, what can help is if we put sort of the two previous pictures together. So we take this circle and that cylinder, we can put them together here, and you get a picture that looks something like this. So now we've got really our cylinder, and then that particular circle there sort of marked on there, so you can see exactly where that is. A lot of times this kind of picture helps me visualize things better. The true answer is really of the intersection of those two equations, or the set of points that satisfy both, is really just this red circle here, though. But you know, the visualization with the cylinder in there helps see what's going on. So that's really the idea, is that circle there. You can see that's just sort of one of the slices if you went along these sort of lines that are circles along the cylinder. Okay, and again, we get a circle of radius 3. It's in the xz plane, that is y 0, and centered the origin. Okay, that's it for equations in R3. We can also do inequalities. One inequality is going to be y greater than 0. So if we look at y greater than 0, it's going to end up being an open half space with y positive. So it's a half space. So instead of like half plane in 2 dimensions, space is the word we'll use in 3 dimensions. And here's an example, or here's a picture of what that looks like. So we had y positive. Note if you rotate this around, x and z, so here's the x, positive z, they can be whatever they want. So we're really going to get planes here. This looks like a box. It's really planes. And then y, this is the positive direction, y is positive. So I think you maybe should be a little bit cautioned here. This makes it look like this picture is like a box or something, but this is actually going to extend infinitely in the y direction, positive y direction, infinitely in x in both positive and negative, infinitely in the z direction, also both positive and negative. So you get a half space, kind of like a half plane, maybe looks like a rectangle if you draw it, but really extends infinitely. Oh, we have this word open here. So open means we do not include the plane y equals 0. That's not really part of the picture here. I mean, it'd be very hard to tell. I guess I actually graphed the closed half plane. But basically we're talking about if this edge counts or not here. So just this plane here, that's sort of the boundary. Do we include the boundary or not? A greater than means don't include the boundary, and a word for that is open, which has certain technical definitions really at higher level classes. If we did a greater than or equal, then it would be closed, and we would include that boundary plane there. Sometimes that'll make a slight difference, not really a huge issue for our sake. Another example here, x less than equal to 2. Again, we'd have to specify this in R3 here. So this is going to be a closed half space with x at most 2. So again, closed is just going to mean we're going to have a boundary plane, and we're going to include that. Again, closed means we do include that plane. And a picture of that. Here, note, this is very much the same picture, but now x, it's a little bit hard to see, but we go over 1, 2 tick marks, and we get our boundary there. So it's a half space, note with the sort of boundary plane not being sort of where the axes are, it's just somewhere. Actually, you could take any plane, even slanted, and get a half space in this fashion here. Okay, another one, we could do 2 inequalities together. We could do x greater than or equal to 0 and y greater than or equal to 0. Now this is a little bit weird. It's kind of like, okay, if there's no z, it'd be in the first quadrant, but then z can range however it wants. You might call this a quarter space. So let's look at the picture here. So here's the picture of what's going on. Something's funny with that picture. I think maybe I need the next one. I think maybe I didn't put that in there. Here we go. Here's the picture. Here. So what we've got here is you could take this sort of, I don't know, quarter space. You could do one in the first quadrant in the XY plane, and then in the second, and then the third, the fourth. So take 4 of these, and it sort of give you the whole space. Now, a sense of what's going on is anything I want to be in the XY first quadrant, XY plane, the first quadrant of that, and then Z sort of varies as it pleases. Now, I don't think this quarter space term I necessarily have heard before. I think people would maybe understand what you're saying here. What's more typical is to sort of do 3, so with another inequality, do 3 inequalities, so x greater than equal to 0, y greater than equal to 0, and z greater than equal to 0. And then we split up, sort of was that picture I showed you before, here, and we get sort of, well, x and y are both positive, and z is positive. So it would take 8 of these to make up the whole of our 3, so you'd sort of have one with x, y, z positive, one with x and y positive, z is negative, one with x negative, y positive, z negative, and so on. So you can pick 2 choices for x to be positive or negative, 2 for y to be positive or negative, 2 for z to be positive or negative, 2 times 2 times 2 to give you 8. In any case, 8 of these would form the whole 3-dimensional space here, and the word we'd use for that is we'd call it the first octant. Now, with quadrants, we have quadrant 1, 2, 3, 4 are very sort of well defined in terms of quadrants, very standard notation. At least I'm not familiar with numbers for octants beyond the first. So there's the first octant, and I think that's, we're going to think of that as x positive, y positive, z positive. But then the second octant, which way do you go? There's probably orders people have. I don't think it's a very well sort of known thing or well recognized thing. So if you talk about, oh, it's in the 6th octant, people might be a little confused. Okay, another inequality. We could do z and mount it below by 0 and above by 3. So 0 less than equal to z less than equal to 3. So this is 3 is bigger than z is bigger than 0. So picture that here. So you get something like this. So x and y here, x and y can vary however they please. Z goes from 0, and then this must be 3 here. So this is going to be closed because we had the less than or equal to there. But you get some kind of a, I'm going to call it a slab. Note this would extend infinitely in the x direction, y direction. You see what you get for the z already. So this, let's call it a slab, maybe with x and y arbitrary, and z just ranges between 0 and 3. Here's another example. We could do x positive, y negative, but now we're going to fix z to be 0. So we're mixing inequalities and one equation. We want all 3 of these to be true. Z is 0 means we're in the xy plane. So we fix z to be 0. And then we need x positive, y negative. So that's going to be, what is that, the 4th quadrant? So the 4th quadrant on the xy plane is essentially what we get, whoops, here. And our picture of that, look at it, is here we have z equals 0. And if we just go into the xy plane, let's see if we can rotate this around a bit. So here's positive x, positive y. I think we lost our letters there. Oh, that's probably good enough so we can see the letters. Positive x, positive y. Note here, up here would be the first quadrant, second quadrant, third quadrant, and this is the 4th quadrant. So this would actually extend forever in the positive x and the negative y direction here. So it's a sort of quarter plane, I guess. All right, so there's inequalities. We have one more, really 2 more concepts here that are related. We're going to talk about distance in R3. So if we have 2 points, now we're just going to label these as x1, y1, z1, x2, y2, z2. So now first point, we have the x, y, z, and we use a subscript for the 1 to say first point. We do x2, y2, z2. The 2 is the second point, and then we have our x, y, z. The formula for distance is very much like in the plane. You take a square root, and then you do the difference of the x's, x1 minus x2 squared, plus y1 minus y2 squared, plus z1 minus z2 squared. So you do the sum of the difference of the x's squared, plus the distance between the two y coordinates squared, plus the distance along the z-axis between the 2 points squared. You add up all those squares and then take a square root. So if we had, say, the points -2, 3, 5 and 0, 4, 1, distance would be -2 minus the 0, that's squared, plus the 3 minus the 4 squared, plus the 5 minus the 1, 5 minus 1 squared. And that gives you -2 squared plus 3 minus 4 is -1 squared, 5 minus 1 is 4 squared. Note here, sometimes you will see this formula given as x2 minus x1 squared, so switch the 1 and 2. Then you'd probably switch the 1 and 2 in all three of these. If you did that, you'd get, say, instead of y2 minus y1, you'd get 4 minus 3, you'd get a positive 1 squared. Now note, switching the 2 and the 1 just gives you a negative number, or the opposite sign that you get in here, but once you square, that's not going to matter. So you may see this as x2 minus x1 squared. It's the same thing. In any case, we continue with this computation. You'll get -2 squared is 4, -1 squared is 1, 4 squared is 16, and that gives us square root of 21, which is some irrational. All right, so that's distance, and now we can use distance to define a sphere. So a sphere, I mean, we want to think of it as really, well, it's the outer shell of a ball. But we can define this as the set of all points that are the same distance from a center point. This is really in three-dimensional space. So the distance, that's what we're going to call the radius, r. Center, we're just going to denote as x naught, y naught, z naught. Here, so we have a point, and we're just finding all of the points that are distance r from that point. And that will define what we think of as a sphere. Note, terminology-wise, sphere is the outside part. If we use the word ball, we're generally going to mean the whole thing filled in. So ball, we'll have to use an inequality. Sphere will be an equation. We just sort of get the outer part. So we do an equation of the sphere. Now we're going to derive this. It's not that bad. So we need to talk about the distance between this point x naught, y naught, z naught, and some arbitrary point x, y, z. We want that distance to be r. So use the distance formula. You get x minus x naught squared, y minus y naught squared, plus z minus z naught squared. Take a square root of that, and that should equal r. Now, square root's a little bit ugly, so we're going to square both sides, and you'll get this equation, which I'm going to put in green because it's really the normal equation of a sphere. Square root just goes away on the left. You get x minus x naught squared, plus y minus y naught squared, plus z minus z naught squared. On the right, that r becomes r squared. So again, it's radius squared here. This should make you think of a circle, but instead of two variables, we've got a third. All right, so let's do an example here. So let's find an equation of the sphere that has center 1, 0, -2, and a radius 4. So we're going to put up this equation again. It's x minus x naught squared, plus y minus y naught squared, plus z minus z naught squared. That should be r squared. And we're just going to plug in what we have. So we do x minus 1 squared, plus y minus 0 squared. So y naught is the 0. Z naught is this -2. So minus -2 would become a plus 2. And r, that's our 4 squared. And then we're going to simplify this down. X minus 1 squared, there's not much we can do with that. Y minus 0 is just y, so this becomes y squared. Z plus 2, I'm just going to leave that squared. 4 squared is 16. So this is our equation of our sphere, whose center is 1, 0, -2, and has radius 4. Okay, another example. Let's find an equation of the sphere that has radius 3, but we're centered at the origin. So this is actually easier. I don't know if I actually said this earlier, but the origin, that's the point where x, y, z are all 0. And so what we get when we use this equation for the sphere is we get a 0 for x naught, a 0 for y naught, a 0 for z naught. Our radius is 3. And when you put this together, x minus 0 is just x, so you get x squared. Y minus 0 is y, so we get y squared. Z minus 0 is z, so you get z squared. And your equation is x squared plus y squared plus z squared equals 9. This is a nice thing to recognize, is when you see this x squared plus y squared plus z squared equals some number, that is the equation of a sphere. Okay, we can go backwards with this. We can take an equation like this Here are some squares with the x, y, z. Note these all have to have the same coefficients. And stretch if we didn't have, like if we had 2z squared or 3y squared. If they were all 5, 5, 5, we could divide by 5 and get back to 1x squared, 1y squared, 1z squared. We're going to take this kind of equation and find our center and radius. So what we're going to have to do is we want to write this as x minus something squared plus y minus something squared, or maybe y plus something squared plus z minus something squared. So we're going to have to complete the square. So the first bit of this, I'm going to group the x terms together, the y terms together, the z terms together. So we get x squared minus 2x, and then y squared plus the 8y. The z is just z squared. There's no sort of corresponding term that's linear in z, just a quadratic term. Now we have the 2. And now when we complete the square, what we want to do is add something inside of each of these parentheses to make the thing inside parentheses be a perfect square. So what's going to happen here, the thing to add is I'm going to take this 2, I'm going to divide by 2, that's 1, and then I'm going to square 1, that's 1. Now when I add the 1 here, I added 1 to the left-hand side of my equal sign, so I have to add 1 to the right-hand side of the equation as well, that's this 1 here. So I add 1 on the right and on the left. That's certainly a legitimate step here. I could add 5 here and 5 here, but that 5 wouldn't actually help us here in a bit. With the y squared plus 8y, what I'm going to do is take half of 8, that's 4, and then I'm going to square the 4, and that gives me 16. Here, so it's half of the 8 is 4, and then 16, and then if I add 16 on the left, I have to add 16 on the right as well. Okay, next step, now this factors as a perfect square. X squared minus 2x plus 1 is x minus 1 squared. Y squared plus 8y plus 16 factors as y plus 4 squared, and z squared is just z squared. And then 2 plus 1 is 3, plus 16, that's 19. So this is really our our sphere equation. And now you can read off the center here. Center is the 1, plus 4 is minus negative 4, so the y coordinate is negative 4. Z squared is z minus 0 squared, so the z coordinate is 0 here. Radius is, well, the square root of the right-hand side is square root 19. Note, sometimes you'll get a question, find the center and radius, and you're given something in this initial form here, and you just read off the answer if that's the case. Although sometimes you have to complete the square or do some other kind of algebra. Okay, so that ends here our notes for this section.